De Morgan's laws. These are laws about the duality of the AND operator and the OR operator. By now you have probably maybe thought about it or had the idea that AND and OR are somehow similar in some way. We have also seen it from their truth tables, that there is something similar between AND and OR. De Morgan's laws allow to represent some operator using other operators. And these are the two laws. This one and this one. The first one is about representing AND using NOT and OR. The second one is about representing OR using NOT and AND. You can probably see that those two laws are really similar. They are just about flipping the OR and the AND. If we turn this AND into OR, or maybe this OR into AND, we get the same formula. These are really important laws. These are really important equations that I advise you to remember by heart. I really think that every programmer should know about those two, which are actually just one. Let's try to understand why is it true. Let's take a look, for example, at the first one. The second one you could do later yourself. Let's take a look at all the possibilities of input. We have input only by two letters, by A and B, only two arguments. We can just count all the possible numbers from 0 to 3. We have 0, 1, 2, 3 in binary. And now we have two other columns. The first one represents the left-hand side of the equation, and the second one represents the right-hand side of the equation. Now let's try every possibility. The possibility of 0, 0 gives 0 with the AND. 0 and 1 gives 0. 1 and 0 gives 0. And finally 1 and 1 gives 1. Now let's look at the other column. We have input of 0 and 0. We have to flip A, which gives us 1, and the flipped B is also 1. Now we have to do 1 or 1, which is 1, and by negating it, we get 0. Same way for the next rows. We have, for example, for this row, the negation of 0 is 1, the negation of 1 is 0. Now when we OR those two results, we get 1, and its negation is 0. The rest of the rows you can probably check for yourself. It is not difficult in any way. Maybe the important thing to remember about De Morgan's law, or laws, is that AND and OR are dual in some sense. They are dual with respect to negation. What does that mean? It means that if we think about two different worlds, about the regular world where every bit is just himself, and another world, the inverted bits world, where every bit is the negation. If we take something from the regular world and we want to go to the inverted bits world, we have to negate everything. Let's try to understand De Morgan's law through this idea, which is basically just an idea. Let's take two different bits, A and B, and now we want to get them to the inverted bits world. So we have to negate each of those bits, and we get not A and not B. Now we somehow, or maybe of some reason, want to invoke OR between those two bits. And we get not A or not B. Now we want to get this number, this result, which is just one bit by the way, to the regular world. In order to do this, we have to negate it. And we get the negation of this expression. By De Morgan law, we know that this expression equals A and B. So basically we can see that we can do this operation A and B in two ways. We can just do it directly, A and B, and get the result, A and B. Or we can do something else. We can move to a parallel world of the inverted bits, and in that parallel world we do OR instead of AND, and then we get back to the regular world where we get the wanted result. So basically what De Morgan's law says is that invoking AND in the regular world is the same as invoking the OR operation in the inverted bits world. We can see here that the AND and OR operations are somehow parallel. They are parallel and dual with respect to negation, which is represented by this horizontal line. All of this diagram is basically a very nice way to remember how De Morgan's law works. Once that you know how to create this expression is just created by getting to the inverted bits world, then doing OR, and coming back from the inverted bits world to the regular world. Once you know that, looking at this expression is not scary at all. You can understand and remember this expression very easily once you know this route. Simplifying statements. Many times we are going to have a very large or complicated expression and we want to turn it into something simpler. There could be many reasons to do it. Maybe we want to understand something or have some kind of insight. It is usually much easier to understand things when the expression is shorter. Usually the meaning is more evident when the expression is shorter. Another reason is efficiency. Maybe you want your computer or your program to calculate something and it involves a very complicated expression. You prefer that your program will calculate a shorter and simpler expression than a long expression. This kind of optimization is something that you as a person have to do. The computer usually is not going to do it for you. Mostly it is not going to do it for you when you use the assembly language. You will have to do it yourself. So let's take a look at two simple examples. The first one, A and B or B. This time we are just going to do the naive thing and check every possible B. If B equals 0, we get A and B is 0 and also B is 0, and we get that the result is 0. If B equals 1, we get A and 1 or 1, which is always 1. So magically we can see that the result actually always equals B. So this expression equals B, which is much simpler. Another example, A and B or A and not B. This time we are going to be a bit smarter and we are going to use the distributive law. The distributive law of AND and OR. And by that law, we know that A and B or not B equals A and B or A and not B. We can see it here, the distributive law. I was talking about this one. A and B or C equals A and B or A and C. Let's go back. Okay, can you see the similarity? It is the same one as the one that I've just showed you. We can further simplify what we've got here. B or not B is always 1, because one of them must be 1. So this one equals A and 1, which just equals A, which is very simple. These two examples are kind of cheating, because I chose those examples to be simplified into something very simple. Sometimes the result is not going to be so simple. Sometimes it is, but sometimes it's not. This is life. The XOR operator. It is also known as exclusive OR. It works like this. A XOR B equals 1 only if A equals 1 or B equals 1, but not both. The not both part is what turns this OR to be exclusive. XOR is basically like OR, but with this modification. You can see that every output bit is the same, except for the one that corresponds to the input of 1 and 1. This bit is different from this one. It is usually marked by A plus inside circle B. This is how we write A XOR B. Another important thing to know about A XOR B is how to define it using OR, AND, and NOT. It actually equals A or B and not A and B. Basically, if we turn it into words, it means that XOR of A and B equals 1 only if A or B and not A and B. Some properties of the XOR operator. I put here this truth table just to remind you how it looks like. The XOR operator is equivalent to addition modulo 2. What does that mean? If we think about 0 as some even number and 1 as some odd number, then we get that even plus odd equals odd. Just like here we have 0 XOR 1 is 1, or maybe 0 XOR 1 on this direction is also 1. And also 1 XOR 1 is 0. So we can really think about it just like addition modulo 2. Or maybe just adding even and odd numbers. Bit flipping. We can use XOR to change bits, or maybe to leave them the same. A XOR 0 always equals A, and A XOR 1 always equals not A. We can see this from this table. We can see that whatever we pick, 0 or 1, if we look at the one row, the bits are inverted. 0 turns into 1, and 1 turns into 0. However, if we look on the zeros row, we see that the inputs are left the same. 0 turns into 0, and 1 turns into 1. That's why we have those two properties. Self-XORing. We are going to see this in the future a lot, so this is one to remember. A XOR A always equals 0. We can see it in this table by looking at the main diagonal. Everything on the main diagonal here is 0. That's why A XOR A always equals 0. Commutative. A XOR B equals B XOR A. This can be seen by the symmetry around the main diagonal in this table. Associative. A XOR B XOR C equals A XOR B XOR C. By thinking about the equivalence to addition modulo 2, This is pretty obvious because this kind of law works on usual addition. Therefore, it should work on XOR too. The distributivity with AND. This is a pretty special property. A and B XOR C equals A and B XOR A and C. How can you remember it, or maybe how can you think about it? AND has the same effect as multiplying bits. We can see here with AND that it is basically just like multiplying. For example, here this 0 equals 0 times 1, and this 1 equals 1 times 1, and this 0 equals 0 times 1. So when combined with the XOR, AND and XOR behave just like multiplication and addition. So this equation is really like this one. The last equation that we can see here, A times B plus C equals AB plus AC, should be pretty familiar to you. So the first one is really the same. It's the same thing. Some words about what we have seen. This is only a very short introduction. It's not a good idea to think at this point that you understand everything about Boolean algebra just because you have seen some of those slides. There is really much more to learn. This was such a short introduction. However, it was pretty important for me to do this introduction just so you will have some kind of foundation for using the operations of XOR and OR and NOT in the future, because we are going to use those operations. And also because maybe if it's the first time that you hear about those subjects, maybe you will be interested and you would like to research more. If it is the case, then these are the subjects that you might want to further research. First one is mathematical logic. This is a very theoretic subject. You can maybe learn it in the university. There are very serious courses about mathematical logic in the university, which eventually gets to the subjects of set theory and maybe calculation of different types of infinities and things like that. It is very interesting. The next one is circuit complexity, which is a subject very talked about these days. And finally, maybe coding theory, where you can learn about very interesting things that you can do with bits. How to code data in kind of efficient way. Maybe add some bits for redundancy to make sure that data is not corrupted when you move it from place to place. And maybe learn a bit about how to compress data. This is a very interesting topic. If you want to research further, I recommend you to take a look at one of those subjects. Summary of what we have seen. Basic statements are either true or false. Not, AND, OR, and XOR are Boolean operators. They could be used to combine basic statements into complex statements. We have seen different representations of those operators and maybe other operators, which are truth tables and Venn diagrams, both of which could be pretty useful to get different kind of information about operators or things that happen to bits. We've seen some properties of NOT, AND, OR, and XOR. For example, that AND and OR distribute over each other. We've learned a bit about the duality of AND and OR with respect to the NOT transformation, and we called it De Morgan laws. Also, we've seen that XOR and AND behave like addition and multiplication. We also seen that we can sometimes use the properties of the Boolean operators to simplify complex statements, which is pretty important. Some exercises. This is a bit of a formal subject. You might think that it is not very practical at first sight, but I did include some exercises, just so that you can make sure that you understood everything that you have learned inside this lecture. The exercises include calculating expressions, building truth tables and Venn diagrams, proving basic properties of AND, OR, NOT, and XOR, and simplifying expressions. I usually say that the exercises are mandatory. In this part, some of the exercises are really theoretic, and the truth is that you don't have to do all of these exercises to be able to move on in the course. But I really do recommend to do those exercises, just so you will get a solid foundation for your understanding about logic and bits. I assure you that it is going to be very useful in the future. So if you do have the time, it would be a very good idea to do those exercises. See you